Now is it visible?
Yeah.
Okay. In last class, we have introduced a characterization tool called matrix algebra. Today, we shall talk about a new characterization tool called reachability tree. Matrix algebra as well as reachability tree, these these tools have been developed to characterize non-uniform CAs. In particular, non-uniform finite CAs, right? Okay, since uniform CAs are special case of non-uniform CAs, so therefore, by these tools, matrix algebra and reachability, we can characterize uniform CAs as well as non-uniform CAs. However, in case of matrix algebra, only linear CAs can be characterized. In last class, we have seen that the matrix algebra can be extended to characterize a special class of nonlinear CA, which is called complemented CA. So therefore, matrix algebra is for linear CA, and extension of the linear CA, that is called complemented CA. Apart from these two classes of CAs, there is a large class of non-uniform CAs, which are generally termed as non-linear CA. For the non-linear CA, obviously, we cannot use the matrix algebra. So this is the reason why this tool called reachability tree has been developed. Okay, before going into the definition of tree and its properties, let us first discuss some useful definitions which are used in the definition of reachability tree. First one is rule mean term. Okay, so although this term we have encountered in some places in previous lectures, let us define it formally. Rule mean term is nothing but an element of domain of a rule. Suppose R is a rule from s to the power m to s. So domain is s to the power m, right? So it has elements, many elements, right? Finite number of elements. Each element of that domain is called a rule mean term, in short, RMT. Therefore, and that element of the domain is actually a tuple, m tuple, right? Right. So, so let us consider this S1, S2, Sm. Okay. So that is an element of s to the power m of the domain. So that is called rule mean term. So in short, each element of domain of R is called a rule mean term. Take an example. This rule table we have shown in previous classes also. So we are taking ECA rules only in this case. So in case of ECA rules, m equal to 3, right? Because r equal to 1, actually a cell in case of ECA depends on left neighbor, self and right neighbor. So m is 3 neighborhoods here. So each rule, in the domain of each rule, it has 3 elements, right? So 0, 0, 0, no, 0, 0, 1, combination of these 3 elements. So from 0, 0, 0, we can get up to 1, 1, 1. So 8 combinations. So each combination, of the states, right? So is called rule mean term, right? So in short, we call it RMT. So you understand that RMT is actually the elements of domain. Now there a question may come, why its name is minterm, rule minterm? In one class we are discussing about minterms, especially while we are discussing the implementation of the CAs. The genesis. Actually, see, while we consider the Boolean logic, right? Then these things 0, 0, 0, 0, 0, 0, 0, 1, these elements, okay, of any function is called a minterm, right? There's classically their name is while we discuss about digital logic, we name them minterm. Now, since these minterms associated with a rule, so this is a term as rule minterm. The term RMT was initially generated, developed for the binary CAs, especially non-uniform ECAs. However, now we have generalized it. So by rule minterm we mean for arbitrary CA, for D-state CA, right? The element of a domain, which is called rule minterm. Right. So normally we represent an RMT by its decimal equivalent. What is that? Say for example 0, 0, 0. If I put 0, 0, 0, it's in this case it's binary number, right? So we call it 0. So 1, 1, 0. So in binary 1, 1, 0 means in decimal it is 6. So if it is trinary number, say if its base is 3, then for example if I get 2, 2, 2, it means 26, right? So so actually I want to mean here that in case of RMT, the convention is they are represented by their decimal equivalent. These other okay. So here I have written in red the values, decimal values of each RMT. And this is also convention. Say for example, rule 165. Say rule 165 for RMT 0. Okay, it is actually 0, 0, 0, 0, 0. So rule 165 is the rule whose argument is 0, 0, 0. Okay. Similarly, rule 165, its argument is 1, 1, 0, means RMT is 6. So this is a way of representing. Sometimes we represent in this fashion. So 165 within third bracket 6. What I want to mean here, that 165 is by rule and 110 is my argument of the rule, and that is equal to 0. Okay. So in this way, this convention we shall follow also. So this is about RMT. Very important term. I mean, and it will be used to define reachability tree. Another important term is reachable, non-reachable configurations. From its name, we understand a configuration is reachable if it is, if it has some predecessor. A configuration is non-reachable if it has no predecessor. You may recall that while we are discussing the classical cellular automata, then we have discussed about Garden of Eden configurations, right? Also, we have discussed Garden of Eden theorems. So, Garden of Eden configurations are the configurations of infinite CA, of a classical CA, which has no predecessor. Here, the same meaning. For the finite cases, we love to call such configurations as non-reachable configurations. So why it is so intuitive, brethren? You may use the term non-reachable, Garden of Eden configuration, but mainly to distinguish the classical notion of non-reachable, Gardner configuration, we have renamed it, right? So reachable and non-reachable configuration, these terms are generally used, for finite cases. Anyway, a configuration C is called reachable if there exists a configuration X such that C equal to Gx. G is my CA, right? G is my global transition function of the CA. So G is from h to the power L to h to the power L is my CA. So this is the definition of reachable configuration. Now obviously, if no such X exists, then C is called non-reachable configuration. We use these two names, reachable and non-reachable configurations, while we define reachability. Well, I take an example. This is a transition diagram of a 4-cell CA with rule vector 165, 73, 290. Right? So this is null boundary condition, right? This is the transition diagram, and you can notice here that say 0, 0, 1, 0, the top leftmost configuration 0, 0, 1, 0, it has no predecessor. So this configuration is non-reachable configuration. Similarly, 1, 0, 1, 0 are non-reachable configuration, whereas 1, 0, 0, 1, you can see that 1, 0, 0, 1, this configuration has two predecessors in fact, 0, 0, 1, 0 as well as 1, 0, 1, 0. So therefore 1, 0, 0, 1 is reachable from some configuration. So this configuration is called reachable configurations, right? Okay. However, in this diagram you can see, also you have seen it before, that here we represent configuration in a different way, actually the same thing but different way. How we have defined configuration before? A configuration is a mapping actually. If I say C is a configuration, C is mapping from lattice to S set of states, right? So it's an assignment. So here we represent a configuration just an assignment. I mean, it's nothing but a sequence of states which are assigned to the CA, to the cells of the CA. So same thing, you understand? So here we represent a configuration C is SI, where you can see here I've defined it, S to the power, SI, I belongs to L. Same definition we have defined before. C is a configuration a configuration C is a mapping from L to S. Is the assignment. We're assigning some states to the cells, and here I am saying, okay, this assignment is there, and here is a sequence of states. Just a different way of looking at the configurations, and by configuration we shall mean the sequence only. Okay, especially while we discuss one-dimensional CA, we like to represent the configuration in this way: the sequence of states assigned to cells of the CA. Okay. Next very important concept is RMT sequence. RMT sequence is nothing but another way of presenting a configuration. So what I've said, configuration is actually a mapping. I have slightly defined it. It is for one-dimensional cases, obviously. It is a sequence of states assigned to the cells. Okay. From the definition, I am getting RMT sequence. Now, I am representing a configuration, same configuration, as a sequence of RMTs. Right? So let me go to the Jamboard. Then I can tell you how can we find the RMT sequence of a configuration. And this is very important. RMT sequence is very important for our discussion. Oh, what happened? Okay. So what I have said, see, first I have said, configuration is nothing but it was actually the initial definition of a configuration, small c. So C is a configuration from L to S. So from this, I want to represent it as this one. Okay, so I belongs to L, and where SI belongs to S. That is okay. From this definition, I can get. So the configuration of the assignment. Now the assignment is written in this way: sequence of states is a convenient way of representing a configuration for one-dimensional case, right? Especially for one-dimensional case, right? Now I'm saying these configuration can also be represented as a sequence of RMTs. How? So let's take an example first. That will simplify our case. Say I am saying a C is like this. Say 0, 1, 0, 1, 1, 0, 1. How many? 2, 4, 5, 6, 7. Okay. Suppose this is my configuration, right? So this is cell number 0. In case of finer, say, let me use a different color. Cell number 0, cell number 1, cell number 2, cell number 3, 4, 5, 6. So therefore, cell number 0 at time, its state is 0. For 1 it is 1, 2 is 0, 3 is etc. So we are talking, we are discussing mainly non-uniform CA, right? Suppose I am saying that rule number 3 is using a rule which has 5 number dependency. That is, rule number 3 depends on 2 cell left and 2 cell right. Okay, so for rule R3, okay, so let me use the other color. For rule R3, what I get, say for rule R3, for R3, it is, my system is binary, so it is 0, 1 to the power, it's 5 numbers, say, so n equal to 5 to the power 5 to 0, 1. This is my R3. Now here, so which RMT is acting on cell number 3? If cell number 3 wants to change its state, what cell 3 will do? It will look its left two neighbors, right two neighbors. So therefore, to rule number R3, its input is 10110, which is actually RMT, which is actually RMT. So it is 010110. Right. So what is it? It's it's decimal equivalent. It is it is 6. Then it is 32. 0, 1, 2, 3, 4, 16. 16 plus 6, say 20, 22. So here rule number 3, RMT 22 is acting. So what we say, how we pronounce it? We say that RMT 22 is acting, IM 22 of rule R3 is acting on cell number 3. So therefore, that's the meaning of this. Okay. So cell number 3 here, it has to use RMT 22 of rule R3 to go to its next state. Very good. So now in this way, I can find out the RMTs of other cells. Now say for suppose, in case of say cell 2, suppose R2 is like this. R2 is like this. Say it has 3 neighbor dependency. Say 3, 2, 0, 1. I mean, say this R2, it depends on these two cells, these cells. So cell 2 depends on cell 1 as well as cell 3. So these three, 3101 is the input of R2. Then which RMT is acting on cell 2? Cell number 2, 101 is actually 5. So RMT acting on 5. Right? So I am getting the RMTs which are acting on different cells. Now in this way, what I'll get? For cell 0, I can get one RMT. For cell 1, another RMT. Cell 2, another RMT. So we'll get a sequence of RMTs. Where from I get it? From the given configuration. So I was saying that it's a different way of looking at configuration. Now let us find it out. Suppose for simplicity, and all other rules except R3, all other rules, it has 3 neighbor dependency. I mean, a cell depends on left neighbor and right neighbor. And the CA is using null boundary condition, right? So therefore, so this cell, it has, so let me use other color again. So here, so I'm saying, say this cell, it depends on left neighbor and right neighbor, it is 0. So 0, 0, 1. So first, for the first one, its RMT is say is 1, RMT 1. Similar way, because 0, its left is 0, right is 1, 0, 0, 1. Similarly for 1, it is 0, 1, 0, it is 2. For 4, recall that what I have said, that I have, for simplicity, I have said that other cells, they depend on left neighbor as well as right neighbor only. Okay, it is 3 neighbor dependency. So it is also for this R4, left neighbor, self and right neighbor. So 1, 1, 0, it is 6. For 5, it is 1, 0, 1, 1, 0, 1, it is 5. And 6, cell number 6, it is 0, 1, 0. Null boundary condition I have considered. So 0, 1, is 2. So what I get here? I get a sequence of RMTs. And what is that? So 1, then 2, then 5, then 22, then 6, then 5, then 2. This is the sequence of RMTs, right? We generally write I have the sequence in this C tilde, right? So this is the RMT sequence. Therefore, it is nothing but another way of looking at the configuration. However, there is a twist. While we are talking about configuration only, Okay, be it this definition or that definition, we need not to know the local rules or the neighborhood dependencies, right? When we know the lattice and the states, okay, states of for the cells, from that information we can get the configurations. However, for a given configuration, if I want to get the RMT sequence, then we need an additional information. If it is non-uniform CA, we are discussing about non-uniform CA. For the non-uniform CA, we need to know the neighborhood dependency of individual rules. That additional information we need to find out RMT sequence of our configuration, right? Okay. However, you may recall that sometime future before we have talked about RNUCA. What is RNUCA? If all the cells use the same radius, I mean all the cells use some rules of same radius. Right? This new CA means this is non-uniform CA, and RNUCA means although the cells may use different rules, but their neighborhood dependency is uniform. It's R. So if it is said, if it is RNUCA, then we need not to pass the additional information like radius of individual, rules. In that case, we need not to know. We need not to supply this information. That what is the radius of individual cells? In particular, if you when you discuss about non-uniform ECSA, non-uniform ECA. Is RNUCA because all the rules, all the cells use the ECA rules, right? How it look like? Say, so rule R is 1 in this case. So if it is said that it is non-uniform ECA, then we need not to tell, not to specify the radius for finding out the RMT sequence. In that case, from the given configuration, we can find out RMT sequence. Otherwise, in general case, you have to pass this, neighborhood dependent information to find out RMT sequence of a given configuration. Okay. So now, how many RMT sequences you can get? It's a very simple question. Number of RMT sequence is actually number of possible states. Possible configurations. Right? Because RMT sequence is nothing but a different way of looking at configuration. If you have k number of configurations, for that k number of configuration, you'll get k number of RMT sequences. Very simple. So total number of RMT sequence possible is actually this one, S to the power L. So it's actually, if you have d number of states, small d number of states, and n number of cells, you have to the power n number of, you'll get, the one number of RMT sequence. So therefore, RMT sequence is a sequence of RMTs. Question is, can we get an RMT sequence which represents some configuration by arbitrarily putting RMTs? Answer is no. You cannot put the RMTs arbitrarily, and you can form sequence obviously, but that cannot that may not correspond to a configuration. Take an example. In my further discussion, we shall consider on only non-uniform ECS, right? So a system is binary system. So and the rules they're using, only the ECA rules. So take an example again. In the previous example, what I have taken. Okay, let me take a new example. So say I'm saying 0, 1, 1, 0, 1 like this. Okay, so null boundary condition I have considered. So for these, what is my AND sequence here? This is 0, 0, 0, 0, 0, 0. It is as 0, 0, 1. Sorry, 0, 0, 1. AND 1. Then it is say 0, 1, 1. It is 3. Say then 1, 1, 0. It is 6. Then 1, 0, 1, 5. Then 0, 1, 0. It is 2. Right? Please check if it's not, then let me know. 1, okay, 0, 0, 1, 1, then 3, then 6, then 5, then 2. Right? So this is the AND sequence. Okay. Acha. One more point I can tell you here, that if there is no confusion, then we can omit these commas. Okay, in this case, particularly for this case, we generally represent this AND sequence without putting comma, like the the RMTs. In case of RMT also, if there is the confusion, then we simply place the elements of S side by side, so like 0, 0, 0. We didn't put comma here. Same thing. So this is generally we write in this way: 1, 3, 6, 5, 2. And in many cases we even don't put this comma, put these brackets also. 1, 3, 6, 5, 2. Anyway, here I want to mean here, so it's okay. These are the sequence and this corresponds to this configuration. Now suppose I want to say I want to form another say sequence. Say for example, say like this. So it is say 1, say 2, 6, 5, 2. So same thing, 1, 3 in 3 is replaced by 2. Again a sequence of some RMTs. Is it a valid, quote unquote valid? I'm saying valid here because it has to correspond. I mean, it has to correspond to some configuration. Can this sequence correspond to the configuration that is built? Our boundary condition is null. So if I want to get 1 here, I am to 0, then actually I know it will be 0, 1. So I am decoding this AND sequence. If I can successfully decode and get an configuration, it's okay. It has decode. So if it is 0, 1, then okay, I can get IMT 1, 0, 0, 1, okay. Then 2. To get 2 here, I have to put here 0, right? I have no other option, 2 is given. So it is okay. This is also 2 I get, 0, 0, 1, 0, 2. Next is 6. Can I get 6 here? After this 0, 0, I have already settled for this cell. So here I can put either 1 or 0. If I put 0, it will be 4. If I put 1, it will be 5. But no way I can get 6. But here 6 is there. So I have to get a 6. So not possible. So therefore, this sequence of RMT, sequence of some RMTs, but it does not correspond to a configuration. So therefore, not valid. So valid. This configuration is valid. Here, invalid. In our further discussion, while we refer RMT sequence, we always refer valid RMT sequences only. So what do we get from the discussion? We get that an arbitrary arrangement of RMTs cannot form an RMT sequence. Right. So we have to follow some particular rule. What is the rule here? You can see while we are finding this RMT sequence for 1D cases, so if window is there, as if some window is there, window is being shifted one room left. We're shifting one room right. You have configuration, we're shifting one room right from this place to that place, just one room right. Now, the content of the window is my RMT for some cell. So for some cell I am getting a window, I am shifting one room just right. I'm getting RMT of the cell I plus 1. And I am getting by just shifting one room right, nothing else. So you can see here, say, for example, here it was 3, this is for this cell number 1, and for cell number 2, what I get for the next number what I get, just one room shift. So therefore, if this is my, if this is my RMT sequence where R is my RMT acting on cell number I, then Ri and Ri plus 1 related. In this particular example, I am saying you that here Ri plus 1 this to be either 2Ri or 2Ri plus 1. Right? So here it was 3 to 6. It is just logic of shifting, one bit shifting, nothing else. Right? It is just, you are shifting the window over as if your window is sliding over the configuration. So therefore, actually, you can think that the configuration shifted left one by one. So it's just nothing but logic of one left shift. And this is true for all binary CA. And in case of ECA, so if it is 6, so for example, if it is 6, then 6 into 2 into 12, but RMT 12 is not valid, so you have to mod it. So in this case, we do mod 8 operation. Right? So this is true for any RMT sequence, right? Okay. So what I've said here. So okay, it is the home task. You find, say, if it is C is say C is Ri, I is L, and say AC is actually this one 0, 1, D minus 1. This is my S. Then what is the relation between Ri plus 1 and Ri? Equal to what? You find it out. Anyway, in my discussion, we shall concentrate primarily on binary C and in particular non-uniform ECS. Why it is so? Because reachability we are going to discuss, we are going to define, that is only for non-uniform ECS. Although the reachability can be developed for any kind of CA, any kind of non-uniform CA, but here we shall discuss only this CA. Okay. So therefore, what is the conclusion? Conclusion is arbitrary arrangement of RMTs cannot form a RMT sequence, right? How can I form the RMT sequence? If I without, so what I've said that from given from a given configuration I can get the RMT sequence. But if you ask me to construct the IMD sequences, it is also possible from the relation between Ri plus 1 is possible to construct RMD sequences. How? I'm giving you an example. Suppose consider say n equal to 4. I mean you have 4 cells here, and says null boundary condition, right? So I'm discussing, as I've said, non-uniform ECS, right? So say first my RMT is 0. From RMT 0, what are the possible RMTs for? What is the possible RMT for next position? So it was Ri plus 1 is equal to either 2i Ri or 2 Ri plus 1 mod 8. Just now I have discussed, right? So if it is first one 0, so possible is 1 is from the 0 I can get 0, and 1, say Ri is 0 here, it is Ri, so I is 0, so from 0 I can get 0 or 1, right? Now from this 0 I can get again 0, again 1, from 1 I can get again, I can get 2 into 1 2 and 3. So this RMT, this for RMT of say first rule, this RMT of second rule, rule R1, this RMT of this RMT 0 1 2 3. Okay, the RMTs of R3 because my CA is non-uniform CA I have considered. So for different cells, different rules are acting. So I'm saying it's a 4 cell CA. In case of 4 cell CA, so 3 cell, sorry, it will be 2. So for the last cell, from the 0, what I can get? I can get 0. Can I get 1? I don't know. Can I get 1? So I can get 1. Why? I shall tell you later. So from 1, I can get 2, but no 3. All the even numbers I can get, right? From 3, from 2, I can get 4, right? I can get 4. From 3, I can get 6. So why it is no? Because I understand that is in null boundary CA. So the last part is always 0. 0 means in any we'll get always the even RMT. Okay, so null boundary condition. So rightmost part is 0. So here I can get from 0 RMT. So these RMTs are from R3. See, by this way I can get the RMT sequences. So we have not considered any state particular any configuration. No? So for the just as an example I am telling you. So here the RMT sequencer, one is here this is actually 0 0 0 0 one RMT sequence. This is 0 0 1 2, and this is 0 1 2 4, and this is 0 1 3 6. So I can get these four RMP sequences, all are valid, all correspond to valid, some configuration. You can check. It is actually 0 0. Configuration is 0 0. Configurations. This is the RMP sequence RS. The configuration 0 0 0 0, and this is 0 0 0 1. This is 0 1 0. This is no, sorry. 0 0 1 0. Yes, right. And this is 0 0 1 1. So the four configurations. You can check, and you don't need to check it because you have followed the logic of constructing an sequence that you have received by analyzing the reverse way. Actually, while you are finding out RMP sequence from the configuration, then you got one relation between Ri plus 1 and Ri that are used here. So obviously you get some configuration, right? So RMP sequence you can get. You can notice one point here, that in this case, particular case, I have started from I have started from IMT 0. From IMT 0, using starting from IMT 0, you can get only these four IMT sequences, not more than that. Similarly, if you start from RMT 1, then you'll get again a set of configurations or set of IMT sequences, and that is exhaustive. Okay, in this case, you cannot get more IMT sequences. All have exhausted. Similarly, if you start from 1 with same logic, similar logic, you'll get another set of IMT sequences. Right. In case of in case of null boundary condition, how many RMTs you can get for rule R0? Okay, RMT 0, how many RMTs you can get? Say, so like this logic here. So always left part is 0 because null boundary condition. Then you can change with this one. So the RMTs for R0 is always 0, 1, 2, 3, because you have the option only, you can put here 0, 0 or 0, 0, 1, like this one, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. Only four options you are having for null boundary case for R0, because you cannot have this 1, 0, 0, no, because null boundary 1 cannot come, right? So just I'm telling you, for R0 only, there are 4 RMTs that are valid. And I'm again using the term called valid RMTs. Valid RMTs. Why I'm using valid? Although R0 has 8 RMTs, yes, but since I'm using null boundary condition 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, these RMTs will never be used. Okay, will never be exercised by R0. So practically they have no use. So to R0 they have been valid because I have set the boundary condition as null. So under null boundary condition, if I want to get all possible RMT sequences, what I should do? I should start with from R0, then from R1. I should start from RMT0, RMT1, RMT2, and RMT3. Okay. So in all the cases, we'll get some some this tree-like structure. Why I'm saying all these things? Just I wanted to tell you here that by doing these things, I can construct RMT sequences in a systematic way. And we shall see shortly that this systematic way will lead us to, to develop a new tool called reachability tree. Going to that part, let me tell you one more term again. Okay, let me use this figure. Okay, okay. So let me rub them. Then so what I want to tell you now, I'm telling you that from the RMT, when I get RMT sequence, then we can associate one configuration with RMT sequence. Actually, we want to associate. How we can associate this? So let me remove them. Just, okay. So here, sorry. So here what I get, the RMT is 0, 0, 0, 0, say 0, 1, 3, 6. So when I get this RMT, say for this, sorry. What happened? Okay, let me copy this part. What happened? Oh, okay. I copied it. Okay, I've copied it. So suppose this is my CA. My rule vector is like this. My rule vector is like this. So here I'm using 165, 73, 200, and 90. Right. So this way I'm using. No, what I'm saying, suppose they're the IMT sequence for the CA, so 4 IMT sequence. So I can associate one configuration with this IMT sequence. How we can do? So it's IMT 0. I can refer, I can go to the rule number 165, IMT 0. This is IMT 0. This is here is 1. So I'm adding 1. So 1, next is IMT 1. RMT 1 of rule 73, 73 IMT 1, here it is 1 means it is 0, you write here 0, and then for 3, so IMT 3 of rule 200, 200 IMT 3, this is 3, this is 1, then 6 of rule 90, 6 is 1, is 1. So I get a pair. This IMT sequence and this one. See, once I get IMT sequence, by applying the rule, I can get this one. So I can associate one IMT sequence and a configuration. Configuration I get from the IMT sequence. And this is actually this IMT sequence, okay, RMT sequence and configuration pair. This is nothing but this is nothing but a you know predecessor. IMD sequence is one way of representing configuration. So this is actually predecessor, predecessor, C, predecessor, and this is successor. So predecessor successor relation I can get. It's very simple. It is very I can directly get it, but it has an implication while we'll define the reachability. Okay. So now let us go back to that part. Let us go back to that part. To to that one to a slide. So these two configurations, sorry, these two concepts are useful for defining the reachability tree. Okay, so I am directly going. If you keep this concept in mind, it will help you to understand reachability tree and how we are defining such a structure and what does it imply. It will be clear. Okay, let us go back to that. So one point I missed here. So see RMT sequence. While I am discussing RMT sequence, boundary condition is important. Okay, this example you see, depending on boundary condition, RMT sequence will change. The example here given, say 110 triple 10 is configuration. Is RMT sequence on a null boundary condition is 3764. But if you use predict boundary condition, it will be 3765. It was 4 in case of, you can see in figure A, it was 3764. But under predict boundary condition, it is 3765. Because we understand that in the predict boundary condition, the rightmost cell and leftmost cell are neighbor of each other, so you are getting a different type of sequence. Mainly the terminating cells, their RTs differ, right? Okay. So these things I have said you. Okay. Next RT sequence and next configuration actually predecessor successor pair. Now come to the reachability tree. So we have discussed all background, knowledges required to define this tree. Actually, reachability represents reachable configurations of a CA. Actually, finite CA, right? It represents only reachable configurations, right? And it uses RMT sequence and configuration pair. Okay. Okay, how it represents only reachable configurations? So therefore, non-reachable configurations are absent in the tree. You understand? Something is absent. Which one is absent? You can detect from the reachability tree. So its name is reachability tree because it represents only reachable configurations of a CA. Take this example. Okay, I shall give you first an example, then we go to the formal definition. Formal definition seems very complicated, but it's not complicated. But at a first look, it's very complicated. So I'm starting with some some example, and from the example, I shall go to the exact the definition. In this case, as I've said, we are concentrating on non-uniform ECS only. And moreover, in my discussion, we shall concentrate only on null boundary condition. So in some way, we're restricting ourselves. It is finite. Okay. And the rules are ECA rules. Boundary condition is null. And we are defining tree, we are going to define tree for this system. Although it's possible to define, any kind of finite CAs, right, for any kind of boundary condition, but we're not going to discuss, right? Because for example, let me give them the example first. So yeah, for an n cell CA, there are n plus 1 levels. It is actually, rooted tree. For this, this kind of CA is a binary tree, a rooted binary tree. Okay, and root is at level 0 and leaves at level n. This is an example of the same CA. It's a tree. See, there are some edges, there are some nodes. You can see here in each node some numbers are hidden, integer numbers, 0. In case of root, so you can get 0, 1, 2, 3. What are these? These are RMTs of cell 0, rule 0, R0. So 0, 1, 2, 3 in this particular example, these are the RMTs of rule 165. Right? Next, in next level, in level 1, just next to the root level, you can see there are 2 nodes. In left side, it is node is made of made by say 2, 3, 6, 7 these RMTs. In that side node, it is made with 0, 1, 4, 5 RMTs. These are the RMTs of the RMTs of next rule, rule 73. Okay, in this way. So the nodes are subset of possible RMTs. Okay, and leaves all are empty. Note here that leaves are empty because it is null boundary condition. For other boundary condition, for example, for periodic boundary condition, they are not empty. They will not be empty. Here, they are empty. And since it is null boundary condition, for this kind of CA, the root is composed with only 0, 1, 2, 3 RMTs, not 5, 4, 5, 6, 7. As I have discussed now, just a few minutes back, that for the first rule, 6, 4, 5, 6, 7, these RMTs are invalid. Okay. Okay, so there's a rule, these are nodes. Now, how the nodes are linked? You can see here the edges are leveled edge. In this particular case, left a node is given, so 0, 1, 2, 3. Its left edge is called 0 edge. Its right edge is called 1 edge. You can see it's marked as 0 and 1. It's always true. Left means 0 edge, right means 1 edge. This is not the level. 0, 1, they're not level. In edge 0, we call it 0 edge. You can see 2 RMTs are written, 1, 3 for 0 edge, and IMTs 2, 0, 2 for the right edge, means for the 1 edge. Why it is so? You can see here for the rule 165, RMT 1, 3, RMT 1 and RMT 3, they gives value 0. Whereas RMT 0 and RMT 2, they give value 1. So they are on 1 edge, 0, 2 on 1 edge, and 1, 3 on left edge. In this way, RMTs, tree is constructed. And if you think that, if you find that there is no RMT which can produce say 1, then that age is kept, that age is not added into the tree. Okay, and that age is called non-reachable age. Actually, that age doesn't exist. So you cannot reach to that age. So here you can see a non-reachable age. You can see here a non-reachable age. Dot line is there. Dotted line is there. That is a non-reachable age. Okay. The tree is supposed to have this age, but due to the rule, there is no age. So it's called non-reachable age. So non-reachable age, it's supposed to have some nodes which do not exist. So they are called non-reachable node. So this is actually a tree of this CA, this 165, 73, 290. Right. Okay, let's again go to Jamboard. So this rough idea I've given you, regarding this tree. Then let me allow to discuss in detail the construction process. Let me go back to Jamboard. Let me copy it. So what I've said here, so I shall draw few edges only. So here a root, it is 0, 1, 2, 3. These 4 RMTs, it makes root. These 4 RMTs make root. These RMTs, under null boundary condition, these values are not valid. These RMTs are not valid. I was using null boundary condition. So rightmost, for the leftmost cell, right neighbor, left neighbor of leftmost cell cannot be 1 because null boundary condition. So they will not come. Okay, in my while I'll try to construct the RMT sequence. Then let's try. See, what is our intention? I have to develop all possible RMT sequences. Anyway, so this is the root. So what I am doing? So it's binary. So since it is binary here, so I'll have 2 children. If it is to say 3 states here, I'll have 3 children, like that one. Now here I see, so left edge is always 0, right edge is always 1. I'm not writing. So it is always 0. It is always 1. We call it 0 edge, right? This edge is called 0 edge, and this edge is called 1 edge. This edge. So I will actually write. So left node is always 0. Anyway, here out of 0, 1, 2, 3, RMT1 and RMT3, they are 0. So what I write here? We write actually it's set. So it is conventionally written as it will be 0 means 1 and 3. So it is 1, 3. So although I have written it as a ordered pair, but it's not ordered pair. So from the very beginning, it is written in this way. So I'm writing here, but it's actually set, right? So it's 1, 3, and here what I get rest RMTs 0 and 2, RMT 0, RMT 0 of 165, it gives 1, RMT 2 of 165, which also give 1. So they're written here. So okay, again this level is set. Okay, so then I get next to now I have to get next to nodes. How we get? See here, since it's 1, I write 2 into 1, 2, 2 into 1 plus 1, 3. I'm writing 2, 3. In 3, 3 into 2 is 6. 6 plus 1 is 7. So here is 2, 3, 6, 7. And in this case, 0 into 1 is 0 into 2 into 0 is 0. 2 into 0 plus 1 is 1. Similarly, 2 into 2, 4 and 5. I think you understand what I'm doing. I'm actually trying to find out all possible IMD sequences. Right? IMD sequences, sorry. IMD sequences, all IMD sequences can be started from started with either IMD 0 or 1 or 2 or 3. So I have written 0, 1, 2, 3, everything in root. Okay, so 2, 3, 6, 7, 0, 1, 4, 5. So these RMTs, these RMTs are for R0. First rule, these RMTs, this is for, these RMTs are of rule 1 in this way. Okay, I am expanding one. Say I am expanding in this one. So 0, 1, 4, 5. So this is for R1. So look at it. 0, 1, 0, 1, 4, 5. Here 1, 4, 5, these are 0. So there will be 0 edge. So 1, 4, 5 on 0 edge. This is 0 edge, this is 1 edge. And here is 1 only. So it's 0, sorry, 0 only. I am to 0 in this case. In this case, you can see it is 1. Right? So I have written here 0. Okay. What I get here? For 1, from 1, I get 2 and 3. From 4, 4 into 2 is 8. 8 mod 8 is 0. And 8, 2 into 4 plus 1 mod 8. So 9 mod 8 is 1. So from 4, I get 0 and 1. Now from 5, 2 into 5, 10. 10 mod, so 10 mod 8. This is equal to 2. And 11, 10 plus 11 mod 8. Sorry, equal to 3. 2, 3 I have already written. Since it is a set, I need to write them again. So therefore, this node consists of 0, 1, 2, 3. These are RMTs. And this one, maybe 0. From 0, I can get 0 to 1. So this is for R2. Let us expand this particular one. So R2, this one. So RMT 0 and R2 and 1, in this case, both are 0. So by construction, what I get? 0 and 1, both are in this side. But here, you have nothing to write. Right? You have nothing to write. So anyway, you get 0, 1, 2, 3. That's another issue. But this part, based on the construction, you can write this part is empty. In this way, we construct. See, in the tree, I should not write this one. But to show you, I'm just putting a dotted line. This doesn't exist. Okay. And so on. This edge is called non-reachable edge. Now, I'm going to tell you the significance of this one. So then, see, you can understand that by developing tree, this kind of structure in this way, what I'm doing here, I'm trying to develop all possible RND sequences, right? All possible RND sequences. See here, in this way, in this case, so I can start with a 0. From 0, I can go here, right? 0 to 0 and 0 to 1. So the edges, they're talking about the RND sequences, right? They are the RND sequences, right? I'm developing the RND sequences, but tactfully, I am assigning a configuration with that RND sequences, with that RND sequence. I'm not simply just writing the RND sequence. We have tagged RND sequences with configuration, next configuration. As a result, we got this, non-existent edge, right? Okay. So now, if I move, okay, let me use a different color. If I start, say, if I move to this edge, move to this path, I'll be able to construct an RND sequence. I'll be able to construct an RND sequence. Along with that, I'll be able to get its next configuration. In other words, while I am, I'm able to construct an RND sequence from the tree, by default, I can get a configuration. But if I fail to get fail to construct a RND sequence following a path, that implies, you can't have that, configuration in the CA. See, in this case, I'm constructing the RND sequence, but what is my next configuration? I have used 1, so it's 1 edge. This is 1 edge. This is 0 edge. So if RND sequences are constructed following this path, then its configurations, associated configuration will be 1, 1, 0, 7, something like that. But what will be this path? Supposedly, this configuration will be 1, 1, 1, 1, 1, 1, but that doesn't exist. It implies that this configuration is non-reachable. You can see here that actually we are tactfully tagging RND sequences and configurations. And the reachability tree, it tries to represent all possible configurations of a given CA. Sometimes it fails due to the tagging. If it fails, it means some edges and some nodes do not exist. These edges are called non-reachable edge, and the nodes are called non-reachable nodes. That's all. This is the basic idea of reachability tree. Right? Here you can see, that see here I'm trying, these are the configurations: 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1. These all are the configurations. Okay, so these all the other configurations. Actually, if I be able to reach to this, to the leaf, starting from root, okay, if I then I get a configuration, right? But if I fail to reach to some leaf, okay, due to this non-existent edges or nodes, then the corresponding configurations are not reachable. From its construction, actually, these A sequences, they are actually the configurations. Okay, so I'm saying that it represents the reachable configurations, right? So number of leaves are the number of reachable configurations. Okay, let us go to the formal definition of this one. This is a formal definition. It looks a bit complicated, but as I've explained, it's not so complicated. Definition: a tree, reachability tree of the boundary from ECA with rule vector R0, R1, Ri, Ri minus 1 under null boundary condition. Oh, I forgot to put a bar here. It should be start with a sequence actually. Rule vector is okay. Okay, let me correct it. Let me correct it. Okay, so this is a rule vector, a null boundary condition. Then it's a rooted and edge labeled binary tree, and edges are numbered. We number the edges in this way. That first is root is level 0, then level 1, level 2, level n. Okay, so in this case, so we write nij. Nij means n means for node, n is a node of level I, and j is the index. Similarly, eij is the we define a level of an edge also, right? So anyway, so eij actually, okay, eij is actually ei2j equal to, so node nij, right? It connects, it has two children. One is in I plus 1 and 2j, that is in I plus 1 and 2j plus 1. So one node, from one node, we get two nodes. So this, node indices that starts from the left side. So first one is in I0, then in I1, and so on. Okay, so at level I, possible number of nodes is to the power I. So in this starts the level index start from j equal to 0, and last one is j equal to the power I minus 1. Okay, and so on. And please note that if some edge node is non-existent, okay, that may have, I mean, say nij may be non-existent. Okay, but that doesn't affect the numbering of the nodes. Anyway, this is E2j and E2j plus 1. We have defined it in this way. And then, and the levels are in ij, they're the nodes, as I've said, they're the subset of set of possible RMTs, right? Or valid RMTs for rule Ri. And the levels Li to j, they are actually nothing but a subset of Nij. Okay. Now, The point is that edges and nodes, they follow some relationship. I have stated the relationship already. They are rated formally. For root n00, n00 is the root. It is always 0, 1, 2, 3. I have said it. And next, look at point number 2. It has said, how can I get? What is the relation between nij and the levels of two edges, right? It simply says that RMTs of Nij, they are divided into two levels, Ni dot 2j, Li dot 2j and Li dot 2j plus 1. That is about point number 2. And point number 3 is saying from the level, how can I get the next level nodes? Okay. And yeah, point number 4 is important. Point number 4 is important. See, just now I have said that for null boundary condition, for the last rule, the odd RMTs are invalid, right? Because the null boundary condition, they cannot come. 0, 0, 1 cannot come for the last rule. If R4, R3 is my last rule, so 0, 0, 1 cannot be activated. Why? 1 cannot come because there is a null boundary, always will be 0, right? So it is 0, 0, 1 and so on. So point number 4 is saying that only mod 2R, if R is my RMT of last previous level, then of the level, so then only 2R is valid, right? And point number 5 is saying that leaves are empty. So what I've said, what I've described you, that is written more formally. So as I've said, it seems very complicated, but it's not so complicated. Okay. So therefore, so this is our tree, which I can get when a rule vector is given and boundary condition is specified, right? Okay, that's all. I have explained, the construction and tree. Let me define two more terms: sibling RMTs and equivalent RMTs. You will notice here that from RMT 0 in one level, I am getting in next level 0 and 1. From RMT 2, I am getting 4 and 5. In general, if Ri is by one level of RMT, so next RMT is either 2Ri or 2Ri plus 1. In my tree, always when 2Ri comes, then 2Ri plus 1 also is there. Okay, so 2Ri for any R, any Ri, 2Ri and 2Ri plus 1, obviously some mod is there. They're sibling of each other. They are placed simultaneously in a node. So we name them sibling RMTs. In general, in a node, if you have this, if you get 0, then you'll get 1 always. Okay. Similarly, consider say RMTs 0 and 4. RMT 0, it produces 0 and 1 for the next level. RMT 4 also produces 0 and 1 for the next level. Right? So we call them equivalent RMTs. Although these have not much use here, but they'll be used in later coming classes. So this is the sibling RMT and equivalent RMTs. So RMTs are classified in this way: sibling RMTs and equivalent RMTs. Okay. Now Few important result. So what we can get from the tree? It's a data structure, tree-like structure. What information it gives? It tells you which configurations are reachable, which configuration are not. We shall see that this structure will help us a lot to decide set theoretic properties, in particular reversibility of a finite non-uniform CA. Here we are presenting very basic results which you directly get from the definition almost. So lemma 1, it is saying that at any level I of a tree, reachability tree of a tensile CA and a null boundary condition, this condition is satisfied. Say from j equal to 0 to to the power I plus 1 minus L, and L, this is always less than equal to the power I plus 1, right? And and when it is for the last for the last one, for the n minus 1, then it is to the power n, less than to the power n. Just let me give just a brief idea why I'm saying so. Let me take the example first. That will help us. See, I have copied that one example. See what I get here. See, from RMT1, I get 2 RMTs. From these 2 RMTs, I get 4 RMTs. So here also from 2 RMTs, I get 4 RMTs. Right. Now these 4 IMTs are distributed again here. So each time it is doubled. From 1 it was 1 3. It is from this 1 3 we get 2 3 6 7, right? And this 2 3 6 7 is divided at 2 7 and 3 6. So 1 3 I am getting 4 here. Here 4. Here also from 2 I am getting another 4. Okay, and what does it say? It says, let's look at this one, this statement. It says that summation of all the cardinality of all the levels, right? It is less or equal to the power I minus 2, I plus 2. Here, what is the value of I? What is the value of I here? What is the value of I here? It is 0. Oh, sorry. What happened? Here I equal to 0. So L 0, 0 is this one. This is 2. And L 0 dot 1 it is actually 2. So what I get, summation of j equal to 0 and 2 to the power 0 I0, so 2 to the power 0, yeah, one statement, 2 to the power 0 plus 1, 2 to the power 0 plus 1 minus 1. Okay, so what is this? This is actually I here it was 0 and j, what is the value? This is actually equal to this 2 plus 2, this 4. It is said that it is to be less than 0 plus 2. Yeah, it's true. Yeah. So I equal to 0 and 2. You can see here it is written. So it is true. Now from this 4 empties here, I can get here how many empties? 1, 2, 3, 4, 5, 6, 7, 8. 8 empties. Its coordinate is 2 plus 2 plus 3 plus 1. So it is doubled each time. So it's the maximum limit. It's the upper limit. Sometimes it becomes less. Why it can be less? The example I have given here. Say for example, take this case. Take this case. Take this case. 1, 4, 5 from 3 IMTs. I supposed to get say 6 IMTs, change to 6 IMTs, but I get 4 IMTs. Why? Because 1 from 1 I get 2, 3. From 5 also I get 2, 3. So it's reduced. Although maximum is upper limit is to the power I plus 2, but sometimes it becomes less. So its relation is less than this one. So here I have shown that it's 2 for I equal to 0. I will tell you it is doubled each time, so it's 2 for all I. Right? Right? Now what happened for this level? For this one, last one, this is actually L n minus 1 dot j, right? And to the power n minus 1 plus 1, n minus 1, like this one. Here in this particular case, you see, according to this argument, it should be to the power n minus n plus 1. If I put here, if I put here, say n minus 1, what I'll get? To the power n plus 1. But since there is the null boundary condition, half RMTs are striked out because odd RMTs don't come. So we get it is less than to the power n. Right? This intuitive idea I am getting, so is informal proof. So we can prove it by using induction. Okay. So this is about a lemma 1. This is about lemma 1. Oh, sorry. Now come to the next result. This is very important. See, lemma 2 and next theorem is also related. See, reachability tree grows exponentially. There is no doubt about it. It grows exponentially. Okay. But point is, for large n, it is difficult to deal with in computer. Right? We claim here that no, for many cases, we need not to grow it exponentially. Why? Because you will see that in each level there are many duplicate nodes. There are many duplicate nodes, right? And number of unique node is limited. And for this case of, for this particular case, it is limited. It is by 15. So number of unique nodes for non-uniform, for non-uniform ECS on a null boundary condition that can never exceed 15. It's always less than 15. So if two nodes are same, two subtrees will be same, right? The information rooted at same subtree, they'll be same. So therefore, in many occasions, we can proceed with a single subtree. Okay. So there's the advantage. Actually, it seems us that it will go exponentially, but it will not. So therefore, we get the next theorem. There exists an efficient algorithm to find out total number of non-reachable configurations of a finite CA. You see that non-reachable configurations, they are exponential in general in any CA. So the number is exponential, right? But if you're asked to find out total number of non-reachable configuration, how can you do that one? You have to check again and again, right? But here I am saying that no, there exists a efficient algorithm for non-uniform CAs. If the CAs, the rule vector is given in polynomial time, it's possible to find out total number of non-reachable configuration of finite CA. In fact, we can design a linear time algorithm. Okay, how you can do that? Lemma 2 is guiding you. Lemma 2 says that at any level, maximum possible number of nodes is constant. I mean, it's a constant. No matter which value, how much, how big you take as n, but your, number of possible nodes in each level is constant. Now, if I develop an algorithm which one by one produce the nodes of a level, and I compute, just note that how many configurations I am getting as non-reachable is possible. So I am not giving you the exact algorithm. So these algorithms are available. So just exploring the reachability tree, right? The structure of tree is possible to find out total number of non-reachable configurations of a finite CA in linear time. Okay, so its proof is actually construction of an algorithm. Okay, and theorem 2 is guiding. Lemma 2 is guiding that it's possible to develop such algorithm. And that's all for today. As I said that for any boundary condition, for any state, it is possible to develop a tree, but we shall not discuss the tree for other boundary conditions or other states, right? It's possible to construct from this one, right? Any question?
So how do you get this 15?
15, right? Okay. As I have said, the sibling current is, they are always placed set of sibling characters simultaneously. I mean, 0 and 1. 1 is sibling to 0, sibling of 0. So if 0 is there, 1 will find there, right? So in here, how many are empties there? So 0, 1 is one pair, sibling empty pair. 2, 3 another sibling empty pair. 4, 5 another sibling empty pair. 6, 7 another sibling empty pair. So in a node, if 0 is there, you'll find 1, 2, then 3, or 3, then 2, etc. So they always appear pairwise in a node. So you have 4 options. Okay, in a node, you can include, you may have this one, or this one, or this one, or this one. So how many possibilities, how many nodes you can construct using these 4 sets? Is to the power 4, right? However, if no node is there, I mean no IMT is included, that is not a case. There is not a node. So minus 1. This 1 is neither 0, 1, nor 2, 3, nor 4, 5, nor 6, 7. So it's useless. So valid valid combination is 2 to the power 4 minus 1 is 15. So number of nodes cannot be more than 15. That is the entity. That's the argument actually. So you cannot have more than 15 nodes. But practically, you see that all the combinations that can't appear. That I'm not doing, here. But upper limit is 15, right? What is said here? It is less than 15, right? It's not less or equal to. Okay. So it will be always less than. But here I am saying that why is 15? Why from I get the number 15? Can never be more than 15, right? It is, less than 15 actually. Less than 15 also you understand why, because all combinations they cannot come simultaneously. I mean, so if you find that an IMT where all the IMTs are present, right, then you'll find that okay, not other combinations are not coming. Okay, from the combinatorics you can, from the construction of the tree, you get that if say all IMTs are present in a single node, then other nodes, other all possible nodes are coming, right? Okay, it's okay.